So I'm going to go through a few exam questions from the NACA Maths Probability Distributions exam question booklet. I'm going to go through 4 exam questions that I think are the trickier ones so that we can get a good understanding of this topic. So we'll start with question 3. Okay, so this is the first question that I'm going to be going over. This is question 3 from the NACA Maths Probability Distributions exam questions. I recommend opening up a separate tab that will go through the video, so duplicate this tab and watch the video of this question. Alternatively, have the booklet printed out, or simply just write down this question if you haven't done so already as we go through it. I recommend having a go at it if you haven't done so already, and the video solution of this exam question will follow. This is question 3. So we're told in this exam question that a probability distribution, remember a probability distribution is simply a table with the outcomes labelled with a small case letter and the probabilities labelled by this. But we're told there's a certain formula for the probability function in this question. And we have to construct for 3 marks. Part A, the probability distribution. That's not too bad, because we're told what the outcomes are. So lowercase x is 1, 2, 3, 4, 5, 6. So we have x, which is 1, 2, 3, 4, 5, 6. So we know what the outcomes are. It says it in black and white. And this formula tells us how to get the probability of each outcome corresponding to different values of x. So the probability that capital X, which is whatever the experiment, so whatever the experiment is, equals to the specific outcome, we have a formula. So when lowercase x is 1, we know what the probability is. Why? Because you just put this 1 into here. Look, that's lowercase. If you put lowercase x being 1 into here, that tells you what the probability is. And that's basically what we want to achieve. That's a probability distribution. So if we put 1 in here, you get 2 minus 1, which is 1 out of 36. So 1 out of 36. The same for 2. Look, all this probability formula holds for every single specific outcome. So when x is 2, you have 2 times 2, which is 4 minus 1, which is 3. I won't actually cancel it down. I'll explain why in a minute. When 3, you have 6. 2 times 3 is 6 minus 1, so that's 5. When it's 4, you have 8 minus 1 is 7. 2 times 5 is 10, minus 1 is 9. And that's 11. And you'll notice if you add up each of those 36, they add up to 1, which is what it's supposed to. You have 1, 4, 9, 16, 25, 36 out of 36, so those probabilities add up to 1. And that is a probability distribution. That's what we're looking for, a list of outcomes and the probabilities. In this question, the probabilities are defined by this formula. So it's very easy to see what all the probabilities are. Okay, part B. So part B asks 2 is strictly less than x is less than or equal to 5. Now this question can be answered very easily given I actually have the probability distribution. So the actual question asks me, what's the probability that my distribution, whatever that is, doesn't actually say what capital X represents, what's the probability that x takes values between 2 and 5 but doesn't include 2? So between 2 and 5 is 2, 3, 4, 5, except we're not allowed to equal 2, so it's just these. Okay? But it's asking for the probability, so I have to add up all the probabilities of the outcomes between 2 and 5 but not including 2. In other words, just add these up here. Okay, so you have 5 plus 7 is 12, plus 9 is 21 out of 36. And let's cancel that down. They're both divisible by 3, so that's 7, and that's 12, so it's 7 out of 12. Again, that just came up by grabbing those probabilities. You look at the inequality and see which probabilities you can include in that range. And that's question 3. Okay, on to the second question. This is question 8 of the same booklet. Part A is quite straightforward, but part B is quite tricky, and I thought it would be useful to go over this question for that reason. Question 8 asks us to find the value of A. We've given the probability distribution, so we've got the outcomes and the probabilities. We have to work out the value of A. So what you have to realise here is that if you know all the outcomes and their probabilities, you have to remember that all the probabilities have to add up to 1. If that's all the probabilities for a certain experiment, if you bunch together all the probabilities, well, they have to add up to 1. So all you have to do is set 1/5 plus A plus 1/10 plus A plus 1/5 and set it to 1. And then what you do is, let's add up the numbers we can actually add up, i.e. the numerical values. We've got 1/5 and 1/5. Okay, that's 2/5. And then we've got 1/10. So if you add that together, you get a half. You've also got an A and an A, which is 2A. So then 2A is a half, and therefore A is a quarter. Once you have A, you can then put it back in, and that's what I'm going to do. So once we have A, I'm now going to replace this with a quarter, and replace this with a quarter. Because now I have the full picture. I have every single outcome and every single probability. Now, part B I think is the tricky bit. So, part B asks as follows. It says, what's the probability that X is bigger than equal to Y? Where Y is 6 minus 2x. It also tells you that a little bit before. Now, this can be quite confusing, as we've got two different variables going on. And what I'm going to suggest is, when we've got two different variables going on, we can actually convert that into one variable, where we're just dealing with x, which is far easier to understand. So what I suggest we do here is, if the probability of x is bigger than or equal to y, where y is this, well, let's put that in there. Before we work out how to answer the question, well, let's rewrite the question. So if probability x is bigger than or equal to y is the question, let me go up here. So I'll write probability x is bigger than or equal to, well, that y is the same as this, so let's put that in. Let's replace y with 6 minus, it tells me y is 6 minus 2x. Okay. And with this we can kind of play around with that. It's just, forget the p for now, just what could we do with this? It's just a standard inequality where you can add stuff to both sides and simplify it. So actually, if I add 2x to this side here, I get 3x. And then divide by 3. So do you see? What looked to be a complicated question actually just ends up being a more standard question. Probability x is bigger than or equal to 2. So x is bigger than or equal to y, put y in, play around with it, basically get x's on one side. It actually just comes out to be probability x is bigger than or equal to 2. Now we can answer that question quite easily. What does that say? What's the probability that my variable x, whatever that is, takes outcomes bigger than or equal to 2? Well, that's just these two here. Okay? Bigger than or equal to 2, there's only 2 and 3, so you have to add up a quarter and a fifth. So the answer is 1/4 plus 1/5, which is 9 out of 20. Okay? So this is question 9, and question 9 is perhaps the trickiest question in the booklet. So this is question 9, same again, have the booklet printed out or duplicate the tab. If all else fails, then just copy this out and have a go at it, and the video solution will follow. This is question 9. So question 9, part A, similar to the last question, it asks us to find the value of k. If you have unknowns in the probability row, you just add them up and set it equal to 1. So look, just add up the k's. You've got k, 2k, 3k, and 4k. Well, we know all of those probabilities have to sum to 1. So we've got 4, 7, 8, and 10. So that's 10k is 1. So k is 1 over 10, which is 0.1, which is what they wanted you to prove. Again, once you have k, go into your table or create a new table and replace it. We're not really interested in algebraic probabilities. We want to have actual numerical values for the probabilities. So that's 0.1, that's 0.2 now, that's 0.3, and that is 0.4. Just check, 4, 7, 9 adds up to 1. So part B tends to throw people a lot. It asks you the probability of x1 plus x2 equals to 4 is 0.1. And we need to show this result. And it says that x1 and x2 are independent observations of the probability distribution. So some of you might be thinking, what does that really mean? So what if you have an x1 and an x2? We're used to when it's just an x. What's the probability x is 2? Okay, it's that. Okay, what's the probability x is bigger than 2? So it's all of these. So x1 plus x2 means effectively you're doing the experiment twice on 2 different occasions. In other words, what's the probability that when I do this experiment, now it doesn't tell you what this experiment is. You could think of it as a 4-sided spinner. Okay, a 4-sided spinner. Okay, you get 1, 2, 3, 4. These are the probabilities. If I were to spin that spinner on 2 separate occasions, what's the probability that the addition of the 2 outcomes that I get equals to 4 comes out as 0.1? Now it tells you it's 0.1. We need to prove it. So the first thing you need to establish is how can I get 4 on 2 separate occasions? I'm going to do this. I'm going to add up the results because it's plus. Okay, so probability of x1 plus x2 means do x1, which is this experiment, do x2, which is this experiment, just on another occasion, and plus means you add it together. So therefore, how can I get 4? There's lots of ways. If you think of this as a combinations exercise. So think about this. We have spin 1 and spin 2. Okay, they're two independent. Okay, they're independent. So on the first go, if I get 1 and I get 3, well, that would give me 4. So it could be 1 and 3. It could be vice versa. That's a separate. Okay, that's a separate possibility, isn't it? Okay, 1 and 3 would give me, adding up, will get 4. 3 and 1. I can't get 4 in any go because then that would require me to get 0 on the other go, and I can't get 0. The only other way to do it is to get 2 on the spinner 1 and 2 on spinner 2. Okay, you can't reverse that because it's the same thing. So you've got 3 different ways of doing it. How do you work out the probability of each outcome? If I got 1 on the first go, that's 0.1. But this is the AND rule in probability. I need to multiply, because if I want to get 3 on spinner 2, which is 0.3, I need these both to happen. When they both happen, they generate a combined score of 4. So 1 is 0.1, 3, which is the same table but for a separate observation, is 0.3. You multiply, which is 0.03 for that line just there. Right? That's less than 0.1 because you can see that's not the only way of doing it. What if I get 3 first, which is 0.3, and then 1 next, which is 0.1? It's exactly the same thing. It's just 0.3 for this line times 0.1. The same thing. They've just been reversed. It's the same thing. Altogether, it's the same thing. You get 0.03 again. 2 and 2. This will be different because we've got 0.2 and then another 0.2. So you've got 0.2 for that one, 0.2 for that one. You multiply and you get 0.04. And what you notice, if you add up 0.03, another 0.03, so I've got 0.06, plus 0.04, you get the 0.1. So then in part C, they generalise for all possible combinations. So what they've done, they've called Y the outcomes when you do x1 plus x2, which means you're doing the experiment twice and adding together the results, and you've got all the possible double up outcomes you can get. Notice we worked out this one in the previous part. We worked out that with 0.1 there was 3 ways you could get a combined score of 4. And they've worked out quite a few of the other ones for us because it's quite time consuming. And part C basically says, fill in the 5 and the 8. So how can I get 5, a combined score of 5, from the original? Yes, from the, see, the x1 and the x2 came from the original. So I want to do 2 rounds of this experiment, add up the score and get 5. How can I get that? Well, it's not that many ways to do it. So 5, so start with 1. I could do 1 and 4. 1 and 4 adds up to make 5. So 1 and 4, you could have 1 and 4. You could do the reverse. It could be 4 and 1, 2 and 3, or 3 and 2. Okay? So there's actually 4 ways this time. And let's work out the probability of each. Remember, to get a 1 and a 4, you need the probability of a 1, the probability of 4, and you multiply. If you need 1 and 4 to play, you have to multiply the probabilities. So the probability of a 1 is 0.1, probability of a 4 is 0.4, so we multiply. 4 and 1 is exactly the same, but it's in the reverse order. But when you multiply, it makes no difference. 2 and 3 is 0.2 times 0.3, and vice versa. And now let's add that all together. So you've got 0.4, 0.08, 0.14, and 0.2. So that's actually 0.2. So that can go here. So that's 0.2. That's the answer there. And let's do 8. Now 8's very easy. There's only one way to do it. I can't use 3, because then I'd need 5. To add up to 8, there is no 5. I can't use 2, I can't use 1. The only way to do it is to get 4 twice. That's the only way I can get 8. So the only way you can get 8 is to have 4 twice. So 0.4 times 0.4, which is 0.16. Now, shall we check we're right? We know that these have to add up to 1. If they're not right, I must have missed a combination. Let's see. 0.01, 0.04, so that's 0.05. Okay, that's now 0.15, 0.35, 0.6, 0.84, and 0.16 makes up to 1. So therefore, that's the answer to part C. Part D asks us, what's the probability that 1.5 is strictly less than this experiment where you're doing it twice and adding up the score is less than 3.5? That now is straightforward because I've got the table for that. It's over here. Okay, x1 plus x2 is represented by these outcomes. So it's basically saying what's the probability that the outcome of that experiment lies between 1.5 and 3.5. So obviously you can't get 1.5, that's fine. So it doesn't include 1.5. What's the very next number we could get? It's 2. Okay? And we can go up to and including 3.5. Now we can't actually be 3.5. That's fine, that's not a problem. Okay? Between 1.5 and 3.5, including the 3.5, the only outcomes that you can collect is the 2 and the 3. Which is this plus this. So 0.01 plus 0.04, which means the answer is 0.05.